Hi everyone. Well, this is the last video for the 2020 school year. We are going to finish up gas laws. I typically do not do gas laws this way, but considering the circumstances, we're going to talk about molar volume of a gas, and then we're going to talk about the ideal gas law. And that will be it for this unit. You'll have a gas law quiz at the end of this unit. You'll have another cooking assignment that you're going to do, and I'm actually going to send you a survey about remote learning experience. On the survey, I just ask that you give me your opinion, give me anything that would be helpful that you've learned in other classes that I can learn from. So let's get started. We are going to learn about what STP is. STP, actually people used to use a ingredient in their gas, in their cars for gas. It was called STP. But in chemistry, we say STP is standard temperature and pressure. So that's why you see the race car driver. So, okay, it's really not this kind of STP. STP in chemistry stands for standard temperature and pressure. So what is standard temperature and pressure? So over here, standard pressure is 1 atm or anything that's equal to 1 atm. So if I gave you a problem and it said standard pressure, you can assume the pressure to be at 1 atm, 101.3 kilopascals, 760 mmHg. All of those are equivalent. The other thing is standard temperature. Standard temperature is 0 degrees Celsius. So what does that mean in Kelvin? It means it is 273 K. So that's what you would substitute in for problems if I were to give you something in STP. STP allows us to compare amounts of gases between different pressures and temperatures. So it's just a standard unit. So make sure you make note that if something says STP, that you use the correct values for pressure and that you make sure your temperature is 273 K. So, moving on, so I talked about that. And so if you see a problem that says STP, those are the values you would put in. But now we're going to talk about Avogadro's hypothesis. You all are familiar with Avogadro's number, 6.02 times 10 to the 23rd. Remember, it's not avocado. And remember, he was not the person that invented or came up with 6.02 times 10 to the 23rd. It was actually just named after him. Avogadro actually did a lot of work with gases. And what he learned in his research that said equal volumes of gases at the same temperature and pressure have the same number of molecules. So they have to be at the same temperature and pressure. So what it's saying is volume, and K is a constant, but volume and moles, so N stands for moles, volume and moles are equal. So as your moles go up, your volume is going to go up. So if you look at the balloon here, I have a certain number of moles there. Say I have 5 moles of gas. So at equal volume, at the same temperature and pressure, say I have 5 moles of gas, and then it goes to 20 moles of gas, your volume is going to increase in the same manner. Okay, that's all that Avogadro's hypothesis is saying. So I'm going to switch over to Smart Notebook and do a couple problems with you. So if you look at the first set of problems, it's under Avogadro's law and molar volume. The first problem says a 25.5 liter balloon holding 3.5 moles of CO2 leaks. So what you're going to do is you're just going to set up a proportion. So I'm going to say 25.5 liters to 3.5 moles is equal to if you're able to determine that 1 mole of CO2 escaped before the container was sealed, what is the new volume? So I'm going to put an X up here for the new volume, but it said if you were able to determine that 1 mole of CO2 escaped. So if 1 mole of CO2 escaped, then it means I have 2.5 moles right here. Okay. So how do you solve for X? Cross multiply and divide. So if I have 25.5 times 2.5 divided by 3.5. So this is the question you got to ask yourself. So if the moles are going down, what's going to happen to the volume? And you should suspect that the volume is going to go down. So my new volume is X is equal to 18 2 sig figs liters. Okay, so let's do one more example. And I'm going to show you, I'm going to set it up the same way, but I'm just going to flip and put moles on top. And just, it doesn't matter which one you put on top as long as you set them equal to the same thing on both sides. So what I mean is if you have 32.8 liter container holds 2.98 moles of H2 at 35.1 degrees Celsius and 2.3 ATM. How many moles of H2 are in 45.3 liter container under the same conditions? So the conditions are the same. So what I'm going to do is I'm going to say, well, 2.98 moles per 32.8 liters. Is equal to, well, the conditions are the same, so except my volume got larger. So if my volume got larger, 45.3 liters, what should you suspect that will happen with your moles? Well, they should go up. So again, cross multiply and divide. So 45.3 times 2.98 divided by 32.8 is equal to 4.11 mole. So now let's look at the second half of this page. It says molar volume. Assume all of the following problems are at standard condition. So this is where we have to make things at STP. And what happens at STP? Standard temperature and pressure. So what can you say at STP? Well, you can also say that 1 mole is equal to 22.4 liters. Okay, so what volume will 0.750 moles of N2 occupy? Well, I can just use this relationship up here. 1 mole is equal to 22.4 liters because all these problems are at standard conditions. So 0.750 mole one mole is on the bottom because you want moles to cancel out, and you're going to put 22.4 liters on top. Moles cancels out. So 0.750 times 22.4, and you are going to have 16.8 liters. So I want you to finish the rest of this page for homework, and I'll load the answers on, and you can check your work. This will be these problems will be on your objective check. So the next law I'm going to talk about is called the ideal gas law. The ideal gas law is pretty similar to the other laws, except the only thing now the ideal gas law contains is the number of moles. So the ideal gas law equation is PV is equal to nRT. P is for pressure, V is for volume, equal sign N stands for moles, R is a constant, and T is temperature. So brings together gas properties can be derived from experiment and theory. So this was actually derived from experiment and theory, and this is how we got that ideal gas law equation. So in the ideal gas law equation, you can solve for pressure, you can solve for volume, you could solve for moles, or you could solve for temperature. R is a constant that will be given to you. And I'll explain that here in the next slide. Temperature must be in Kelvin. N is in moles, V is in volume, so it has to be in liters, and pressure is in ATM. So P is pressure, V is volume, T is temperature, N is the number of moles, R is a constant called the ideal gas constant. Now, there's actually several different ideal gas constants because the ideal gas constant is based on the pressure units. So you should know by now your pressure could be in ATM, it could be in mmHg, it could be in PSI. However, for the sake of ease, we are going to use one constant for this experiment. So instead of learning a different value for R for all of the possible unit combinations, we can just memorize one. And you're not going to memorize it, you're going to have it with you. So this is the constant. 0.0821 liters times an atmosphere divided by a mole times a Kelvin. Yep, I know it looks a little big, but this is the reason this 0.0821 is what it is because it needs to be in units of ATM. This is the constant we're going to use throughout. So, how much N2 is required to fill a small room with a volume of 960 cubic feet or 27,000 liters to 745 mmHg at 25 degrees C? So how much N2? So it's really asking how many grams of N2. So you are going to have to solve for moles first. So we're going to use the ideal gas law equation. So if you look up here in red, if you think I got to isolate the N, I got to isolate N, which means I got to get it by itself. That means I'm going to divide both sides by RT. So moles is equal to PV over RT. So get all your data in the proper units. So what does that mean? Millimeters of mercury has to be switched to ATM, and that's because of the gas law constant that we're using. 25 degrees Celsius has to be converted to Kelvin, so that's 25 plus 273. So your new temperature, or the converted temperature, is 298 K, and your new converted pressure is 745 mmHg divided by 760. So that will give you a pressure of 0.9 ATM. And we always know that R is 0.0821 liters atmosphere mole K. So now plug in those values. So we're going to divide both sides by RT. Now, this is the setup. Pressure, 0.98 ATM. This is 27,000 liters, or 2.7 times 10 to the 4. This is your R constant that's given to you, and this is your temperature in Kelvin. So let's go through and see what needs to be crossed out, what units. So you are going to cross out ATM. ATM will be crossed out. liters will be crossed out, and temperature will be crossed out, K. The only unit you have left is moles. So you will end up with 1.1 times 10 to the third moles. And then from there, how do you go from moles to grams? Well, you have to multiply by the molar mass. So you're going to take 1.1 times 10 to the third times 28 grams. So if I did that times 28, that gives me 30,800 grams, which is roughly 30 to 31 kilograms. So this is page number 11 in your homework packet, and here's some examples of ideal gas law problems. So this is the equation, PV equals nRT. In class, I would call this Pervnert. And this is your R constant that you're going to use. So it says how many moles of radon will occupy a volume of 12.7 liters at 0.95 atm and 45 degrees Celsius. So the first thing I like to do is I like to take the equation PV equals nRT and set it up so we can determine what we're trying to find out. So we're trying to find out moles here. N is moles. So we're just going to do like we did before. We're going to divide both sides by RT. So PV over RT is equal to moles. Okay, so pressure. We know what the pressure is. It's 0.95 atm. Times the volume, which is 12.7 liters, divided by R. This is the value we're going to use. So we're going to use 0.0821 liter times an atmosphere divided by a mole K. Times temperature. If you notice up here, my temperature is in Celsius. So I have to say 45 plus 273 will give me 318 K. Now go through, I'm going to go through with another color, and we're going to cross out what units cancel out. So ATM cancel out, liters cancels out, and K cancels out. What are you left with? Moles. So when you put this in your calculator, you can put it in as parenthesis 0.95 times 12.7 close parenthesis divided by 0.0 parenthesis 0.0821 times 318 close parenthesis. And you, because of sig fig, so there's 2 sig figs in 0.95, there's 3 in 12.7 liters, there's 3, and there's 3 in the temperature, so it'll be 2 sig figs. So your answer is going to be 0.46 moles. So what I want to do is I actually want to do the next problem. I'll do one more example with you. Because I want to do this one because if you notice, the pressure is in kPa. So I am solving for liters. So PV is equal to nRT. So L is liters, so that would be your volume. So how do I get V by itself? I'm going to divide both sides by P. Okay, so volume is equal to nRT over P. The next thing I need to do is get rid of kPa. So there will be 1 mole at 101.325 kPa. Well, if you remember from our pressure conversions, 1 atm is equal to 101.325 kPa. So we're going to substitute 1 atm in for that. So moles is 1 mole times R. So I'm gonna put a time sign there. 0.0821 liter atmosphere mole K times temperature. Temperature is 0 degrees Celsius, so that means it's 273 Kelvin. Divided by pressure of 1 atm. So I'm going to change the color of my pen, and I'm going to say atm cancels out, K cancels out, mole cancels out. What am I left with? I'm left with liters. So we're going to do 1 times 0.0821 times 273 divided by 1, which will give you a V equals to 22.4 liters. Well, that makes sense because we just talked about that. If your pressure is at 1 atm and your temperature is at 0 degrees Celsius, that means your volume will be equal to 22.4 liters. So this concludes this lesson. This is all we're going to cover for gas laws this week. Again, I will have a Google Meet, and I highly recommend everyone show up for the Google Meet because I want to have conversations about grades and how they're calculated and what's your preference. So I hope you all have a good weekend. Make sure you get your work done because after next week, the last week of school is makeup. So if you get all your work done on the final week, then you're off a week early. So get all of your work done. I hope you guys have a great day, and I will talk to you soon.